Good afternoon, class. Today we're going to look at the chords of a circle. We've looked at tangents and we've looked at arcs of a circle. And we've talked a little bit about measures there. But now we're going to look at chords in particular. And how they relate to the other parts. The arcs, the tangents, what's so important about chords. So in this section, the first thing we're going to take a look at is what we call theorem 10.3. It's pretty straightforward. In the same circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Remember that IFF means if and only if. It's a notation form for that statement. But the idea here is if I have a circle, and I know that two arcs are congruent, well, the chords associated with those arcs are also congruent. Similarly, the same is also true for if the chords are congruent, then the arcs associated with them are also congruent. So let's take a look at what that means. If I would have a circle here, and I would have a chord here, and a chord here, and I knew these two chords were the same length, well then their arcs would be the same measure, they would be the same size, because it's of the same circle. So if this was A right here at this point, if this was B, C, and D, I can make two statements. If I know that segment AB is congruent to segment CD, well then I could also say arc AB is congruent to arc CD. This is a two-way street. One causes the other to be true. And that's what the statement says. So if the chords are congruent, the arcs that they're associated with are also congruent. Alright, so let's see how we might be able to apply this. Maybe we're given some sort of logo, like maybe something like this here, a triangle inside of a circle, which by the way, this would be called an inscribed triangle, because all the corners touch the edge of the circle. So let's see what they ask us. They ask us a question along these lines. They say, hey, find the measure of the arc given information provided below. They tell me that the length of segment RS equals the length of segment ST, and that the measure of arc RT is 70 degrees. And they want us to find the measure of arc RS. So first let's redraw the picture. Draw a circle, then draw a triangle. If they did not give me a picture, I would have drawn this anyway, if they would have told me how to draw it. Label what we know, R, S, and T. Now I know the length of segment RS and the length of segment ST are the same, so I'm going to mark. I also know that the measure of arc RT is 70 degrees, so out here is 70 degrees. And what I'm looking for is the measure of arc RS. So I'm looking for the measure of this arc over here. Well, last section we were talking about central angle, but I don't see a central angle here for X. Oof. I think I see something here. What if this chord and this chord were the same size? Oh, they are. Well, wouldn't that mean that this arc and this arc would be the same size? Yeah, it does. That's what the last theorem just told us. So that means if that's X degrees, this is X degrees. Now, I know I haven't gone over this yet, but all the measures of a circle will add up to be 360. So X plus 70 should be 360. So let's do X degrees plus 70 degrees, and that should equal 360 degrees. One unknown? Solve. Degrees is no longer needed, so I have 2x plus 70 equals 360. Subtract 70 from both sides, 2x equals 290, and x would be 145. So now they asked me for measure of arc RS. They didn't ask me what x equals. They wanted the measure of arc RS. So when I report my answer, measure of arc RS equals 145 degrees. Circle it, box it some way, let me know what's the answer. And there we go. That's example 1. Alright, let's look at another one. I ended up using the same picture, so we're going to use the same picture. In fact, this is example 2. If you did not notice a change in the slide, there is an example 2 at the top, and I changed some information. Now, I'm going to erase the parts that I changed, so that way we can look at this again. It says, find the measure of the arc given, information provided below. So they, again, tell me that length of segment RS equals the length of segment ST. So I know those two chords are congruent. They also tell me that the measure of arc ST is 70 degrees. And then they want me to find the measure of arc RS. So they want me to find this over here. Hold on a second. The last theorem said if the chords are congruent, the arcs containing those chords, so this arc and this arc, have to be the same size. Wait, so if they're the same size, that means they have the same measure. If that's 70 degrees, that has to be 70 degrees. Yeah, so this is just as simple as saying x equals 70. But I wasn't looking for x, I was looking for measure of arc RS. So even though I had x equals 70, I'm going to put measure of arc RS to be 70 degrees. Yeah, this one was a little bit easier than example 1, but this is what you're going to, for the most part, do. All the measures of an arc will add up to be 360. If you see two chords that are the same, you know that the arc measures are the same. And vice versa. If I knew the arc measures are the same, I know the chords are congruent. Alright, that's pretty much it for this one here. Yeah, you'll see a little bit tougher examples, but that's the main idea. The next thing that we're going to look at is the relationship between a chord and the diameter. Now, we're not just going to look at any old diameter, and we're not going to look at any old chord. We're going to look at specific ones. And in this case, we're only going to look at ones that are perpendicular, because those are the ones we are focusing on, because those are the things that we can actually say something about. So if one chord is perpendicular bisector of another chord, the first chord has to be diagonal. Alright, so what does that mean? If I had a circle here, and I had two chords intersecting in it, one here and one here, and I knew that this chord perpendicularly bisected that chord, my horizontal chord here is actually a diameter. It has to be. Two conditions have to be met for me to know that's a diameter without knowing it goes through the center. See, did I ever label the center of the circle? No. But just by knowing that's perpendicular and that cuts it in half, I know without a shadow of doubt that this chord horizontally has to be a diameter. So, if one chord is a perpendicular bisector of another chord, that chord is the diameter. So, if it cuts it in half and is perpendicular, it's a diameter. Yeah, it goes through the center somewhere around here. It's not drawn, but I know it without even seeing it. Alright, an example that you might see from this theorem is this. Determine if the segment AB is a diameter. So I give you a few different pictures. Well, the condition for me to know if it's a diameter is that, first of all, it's perpendicular to another chord. Secondly, it cuts it in half. So that's the condition for me to know it's a diameter. Option 2, I know it goes through the center. If I look at both pictures on this example here, I don't see a center dot anywhere. So I don't know if it goes through the center, or I can't at least visually see it. So in this case, I'm going to say I don't know it's a diameter that way. I have to go with option 1. Does it cut a chord in half, and is it perpendicular to it? So let's look at the left one here. First question, does segment AB here cut this chord in half? Oh yeah, the top half is 15, the bottom half is 15. That's perfectly in half. So it bisects the chord. Is it also perpendicular? Where's my mouse? There we go. Well, that symbol there does mean perpendicular. So it's perpendicular, it's a bisector. The one on the left is a perpendicular bisector. How about the one on the right? Well, look, this mark here and this mark here means it's congruent. So it cuts it in half. But is segment AB perpendicular to segment CD? Well, visually I want to say yes. But there's no symbol. So at best I could say not enough info. At best. So it's either not enough info or it is not a diameter. And in this case, because I don't know if it's a 90 degree angle, and if I don't know if it's an 89 or 91 or 90.01 degree angle, I would put not enough info because I think it's honestly a better answer. If you knew for sure that wasn't a right angle, I would say it's not a diameter. but there's not enough info. So the left one's a definite yes, or is sounding yes. The right one, there's just not enough information. If I knew segment AB and segment CD were perpendicular, different story. But I don't. Alright, another thing that we're going to look at in this section with chords is if I know I have a diameter of a circle, and I know it's perpendicular to a chord, I know it cuts the chord and its arc in half. It bisects both the chord and the arc. Again, that word bisects basically means divides into two congruent parts, cuts it in half. So, if I had a circle here, and I had a diameter, this way I know it's a diameter because it goes through the center. Okay, so that's the center. So that's definitely a diameter. Alright, I also know there's another chord over here. Right there. And I know it just happens to be perpendicular to it. And this is what the theorem says. That's the condition. If I see this, then, and only then, can I say this. This segment and this segment have to be the same. And this arc and this arc have to be the same. So let's put in a few letters here. A, B, C, D, E, and F. Segment segment BF is a diameter, and it's perpendicular to segment CA. Because I know those two things to start with, I could then say segment CD has to be congruent to segment DA, and I could also say that arc CB is congruent to arc BA. This is what I can conclude if I know a diameter is perpendicular to a chord. Yep, that's what this theorem allows me to do. So, I could ask you a bunch of questions now. Find the value of the variable in circle P. Well, first of all, I look. In all those circles, do I have a diameter? Yeah. Do I know that diameter is perpendicular to the other chord? Yeah. So I can use this theorem here. I'm going to be using the idea that the chord is cut in half and that the arc is cut in half. Let me redraw these circles. Alright, so in all of these, diameter is perpendicular to my chord. So automatically, congruent, congruent. Diameter perpendicular to the chord, congruent, congruent. Diameter hold up. Both of these are diameters. Wait, these are radii then. This is a radii, or a radius, this is a radius, this is a radius, this is a radius. So those will just be setting them equal to each other because all radii of one circle have to be the same length. But anyway, back to this one. If I made this one marked congruent, then that means I can just set 2x equal to x plus 7. So for x, subtract x from both sides, x equals 7. Alright, nice. Let's look at the one over here. Again, the mark here tells me I can set them equal to each other. So let's do that. 5y plus 5 equals 3y plus 7. First step, get all the y's to one side, so subtract 3y from both sides. 2y plus 5 equals 7. Subtract 5 from both sides, I get 2y equals 2. That's multiplying, so divide both sides by 2, y equals 1. Nice. And the last one, yeah, I don't have those markings, but this here, each segment is a radius. So this segment, this segment, this segment, and this segment are all the same length. Oh, so then I just do this. 6x plus 9 equals 8x minus 13. All x is to one side, so subtract 6x from both sides. 9 equals 2x minus 13. Get x by itself, add 13 to both sides. 2x equals 22. Get x by itself here, so not multiply both sides by 2, but divide both sides by 2. X becomes 11. And there we go. This is using the idea that A diameter that is perpendicular to a chord cuts it perfectly in half. It bisects it. There's one last thing that we need to look at for this section, and that is, what about chords that are the same distance away from the center? So in the same circle, or in congruent circles, two chords that are congruent if and only if they are equidistant from the center. Did I say equidistance? I have this horrible habit of saying equidistant as equidistance. It's supposed to be equidistant. If you hear me ever accidentally say equidistance, I'm making a mistake myself. I always try to catch myself, but I only catch myself a small percentage of the time. Equidistant means the same distance from the center, or the same distance from a point. So in this circle, or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So in this picture here, you see chord QR and chord ST. Now, for this segment UC and segment CV to be the distance from the center to the chord, it needs to be perpendicular to the chord. If this is not perpendicular, it is not the distance from the center, period. It's some other distance, but it's not the distance from the center. Also, segment UC and segment CV have to be the same length, and they have to be perpendicular to the chord. If that is true, I can now say without a shadow of a doubt that segment QR and segment ST have to be the same exact length. Alright, let's look at one example and we should be done with this section. Here's the question. I want you to find three things in this picture. I want you to find the length of segment QR, the length of segment QU, and the radius of the circle C if you know these three things. Length of segment ST is 32, length of segment UC is 12, and length of segment CV is also 12. So let's redraw the picture. Alright, so they're asking us for three different things. They want to know the length of segment QR, they want to know the length of segment QU, and they want to know the radius of the circle. So these are the three things they want from us. Well, I look. Chord ST and chord QR have the same length from the center, and it is the distance from the line to the center because of that perpendicular symbol. So these two chords are the same distance from the center. The last theorem I just said allowed me to say segment ST is congruent to segment QR because they are the same distance from the center. So I already have QR. It's whatever segment ST is. Well, that's 32. And now comes the tricky part. I have to somehow justify how I know that segment QR or segment QU has a certain length. Here's the idea. If I would extend this line here through U here, and I would just do like a dotted line here, and I would do a dotted line over here. This big segment is a diameter. Wait. That's a diameter, and it's perpendicular to segment QR? Well, if it's perpendicular to segment QR and it's a diameter, that tells me that it cuts the chord into half, and it cuts the arc into half. Hold on. If this is cut in half, if I know the full length is 32, then half of the length for QU is 16 and 16. There I go. There's my justification. It's 16 because that's a diameter. That's a chord. It's perpendicular, which means the chord has been cut in half. Awesome. But now they ask me the tricky question. What's the length of the radius? Well, I don't actually have a segment anywhere on here. That is the radius. So here's what I'm going to do. I'm going to draw a convenient radius. Hopefully one that makes a right triangle. So I look. What if I drew from the center here to R? That would would be the radius. Oh, I see it now. I just made a very convenient radius. So convenient, in fact, I'll be able to find it. If I erase everything but that right triangle right there, I think I know how to find the radius, or r. I know two sides. I know that's 12, I know that's 16. I'm looking for r. Pythagorean's theorem, another chapter 7 problem. 12 squared plus 16 squared equals r squared, because r is the hypotenuse. So 12 squared is 144. 16 squared is 256. And that's equal to r squared. I add those two together, I get 400 equals r squared. R is 20. Yeah, plus or minus 20, but negative 20 doesn't make sense here. So r is 20. And there I go. I found all three. I used quite a few different things. The first one, I used the most recent theorem. If it's the same distance from the center, the chords are congruent. Then I used the one just before it. If I know a diameter is perpendicular to a chord, that chord's cut in half. Yes! And then the last one, I drew a convenient triangle to find r. And there I go. I have everything I need. At this point, I believe we're done with this section. You should have a pretty good idea about chords. So we've looked at tangents, we've looked at measures of arcs, and now we've looked at chords and the relationship with arcs. We're going to go a slightly different approach from here on out. At least for the next two sections, we're going to look at just angles. Before this, we've been kind of looking at new shapes and how they're related, but now we're going to focus on angles. All right, till next time.